There's a quick question.
Yeah,
Because you're giving the overall number, can you give us a rough indication, stomach feeling about the wavelength dependence? Or if you're saying we're dealing only with dealing only with reflective or near infrared, is there some wavelength dependency in the uncertainty?
there is. And so that's, I had it in one of the bullets and I didn't highlight it as I was rambling on in my usual manner. One of the key things I want to do into the future is include spectral. And what's nice is, as I do more projects, the Clario project, which I'll talk briefly about this afternoon, is a climate mission, and we're doing imaging spectroscopy for that. We have to be able to prove what the air budget is at all the measurement wavelengths. And that's forcing us now to start reconsidering how we do our air budgets. So for instance, I might break out the atmospheric component into an absorption and a scattering component at the very top level, so that I can keep track of those errors separately so that I know which one I have to improve the next time. That's the advantage of the more boxes you have on that first level, the easier it is for you to keep track of where you need to be doing your work. And if you want to skip something, you can skip it more easily and you know you've skipped it, as opposed to when it's down here and it's part of 4 or 5. You can leave out the absorption part easily and nobody will know why you did that. So the fast answer is, yes, we need to do spectral.
Okay.
I'm trying to be less of an old scientist that gives that 5-minute answer to a 30-second question. I've yet to be the scientist, and we all know them, that asks the 5-minute question that's not a question. Those are the ones, if any of you that see me do that, if I get old enough and I'm still going to meetings and I do that, I ask a 5-minute question that is not a question, come up to me afterwards and tell me, you need to stop coming to meetings because you're not asking questions anymore. And I'm sure all of you will have the courage to do that. That's right. Site selection. Examples of current sites and how they were selected. This is nice because, again, it plays on my old age, and I can now tell stories, because that's all this is telling the stories. And it also is about, most of it's not my fault, don't blame me. And this is going to be a stroll down history as to why vicarious calibration used White Sands, and then used Ivanpah Playa, and then used Lunar Lake, and then went to Railroad Valley, when the people who were doing the work lived at this red dot. And we're traveling over here to the far east, not quite as far as this, but and then over to the west, and then over to the north and west, and how we came about this. So the original, White Sands test site. If you know anything about reflectance space calibration now, you should look at that image. And this is a 3-band mix of Landsat 5 data. And it's a mix that includes the shortwave infrared bands because of the geology. You should be going, who in the world ever thought that White Sands was a good test site? Because in the visible, it looks like this. Very boring, very gray, very white. In the shortwave infrared, that site is right about here. That's a lot of color. And granted, when I did this, I purposely did the stretch to make it look pretty, because I printed it and hung it on the wall in my office, and we wanted something that was very striking. But it also then, and that was back when I was an atmospheric guy, just learning how to do image processing, and I didn't quite understand the error budgets. And then I realized, well, this is just really proof that we didn't do a great job of picking a site. This blue over here, it has a visible band, and then the shortwave infrared, it means that these are sand dunes, and this is all really bright sand, and everything else is really dark. Not a good choice. Lots of color and odd blues and oranges. Not a good location. All of this is vegetation out beyond, so it's really the White Sands proper is this section here. So why White Sands? So all the things written there, and I can just start talking because I know the story pretty well. And you can read it if you'd rather not listen to me, but the whole idea was, back in the early 1980s, the the U.S. was starting to launch with the USGS a new round of Landsat systems. And the idea was we wanted to do agriculture with it. And the agricultural people realized that in order to do quantitative studies, how much wheat is being grown, we needed to have quantitative information from the satellites. And the only way to do that was calibration. And it was the fortuitous combination of a very intelligent person living in Phoenix named Ray Jackson, working for the USDA in Phoenix, and Phil Slater of equal intelligence working in Tucson, and the two of them are about 120 kilometers apart. So relatively close in proximity, and they had been working together on several projects. The validation work that was being done by the USDA in Phoenix relied on reflectance panels. Those reflectance panels were calibrated by Phil Slater's group at the University of Arizona in Tucson. So that's what started the relationship. And then they got the idea of, well, how do we know that the calibration system for Landsat is going to work on orbit? Nobody's really ever used lamps. Nobody's ever really done any of this before. Is there a way that we can check the instrument once it's launched? Prior to that, just shortly before that, the geostationary systems, somebody had come up with the same concept, the same question, to try and figure out how to do the calibration of the geostationary systems once they were up. But it was at the much longer wavelengths. It was out into the microwave even. And they were looking at thermal effects. But Slater and Jackson figured out pretty quickly that you could do a similar idea was, what if we had a panel, a reflectance panel on the ground? Well, Ray Jackson was going to western New Mexico, or eastern New Mexico on a regular basis. They'll show up basically, White Sands is right here, tucked away, and right next to it, just to the left, just to its west, was what was called the Hornada Test Range, and it was an agricultural validation site. And so they were looking at Landsat imagery from the past, from MSS, and when you do that, you see this big, bright white thing, because MSS had no shortwave infrared bands, it was just visible. So you saw this big white thing, and they said, you know, that looks like a reflectance panel. You know, what if we could get the reflectance of that? And we know this guy over in atmospheric sciences, John Reagan, who builds these solar radiometers. What if we borrowed one of those solar radiometers to measure the atmosphere? And we stole a radiative transfer code from Ben Herman in atmospheric sciences, who was my advisor, and so was John Reagan on my MS work. And basically go out to this site and make measurements and then predict the top of atmosphere radiance and do a calibration. So this site was selected because they saw it in the imagery, it was close to another test site, and it was near Tucson, Arizona. And it looked like a panel. So we went to Chuck site. And it's called Chuck site because it was the C site. And in American, in kind of lettered, it's Alpha, Bravo, Charlie. Charlie is 2 syllables. We do not like long words in the military in the United States. So we shortened it to Chuck. You'd think these are fake stories, but they're real. So the reason Chuck site was selected was Phil Slater understood that characterizing a set of dunes was going to be doomed by BRDF effects. So there was some science that actually came into play. And then it was, okay, let's go to places where it's flat, the alkali flat areas of White Sand. So here's some dunes over here, let's get away from the dunes. Well, there's some buildings here. Is anybody using those buildings on a regular basis? The military goes, no, just periodically you have to leave and we're going to bomb the area, but otherwise you're okay. And there was electricity, and that was the driver. So there's a road, and there was electricity, and the really fun thing is down here to the further south was where they tested the stealth bombers for radar backscatter. And they had this thing that basically could put the airplanes underneath this cover so they could hide them from the spy satellites, and then they were doing radar backscattering measurement. If you go even not quite as far back, over here was where they were doing what's called the Delta Clipper. And it was a vertical takeoff and launch rocket back in the late 90s. And then up here is the shuttle landing strip. So we got to see a lot of interesting things going to this site. So I liked this site. It was a lot of fun. And it was fairly close, but its spectrum was really bad. So Ivanpah was next. Well, we're going to do real science in this one. We're going to really pick it properly this time. It was selected because people from JPL who like to gamble drive from Los Angeles to Las Vegas. And when they drive from Los Angeles to Las Vegas, they take this road right along the upper left there, Interstate 15 into Nevada, and you go past this big, bright drive lake bed. And so when they were talking about how to calibrate avarice, somebody says, there's this thing, when I go to Vegas to go gambling, there's this thing, we could just stop and just set up some equipment there. It should be, we know what these guys in Arizona have been doing for the last 5 years. We ought to be able to do the same thing at this Ivanpah Playa. That's how it got selected. The reason it got selected for the University of Arizona was we were doing some work with HIBEX. And that was an airborne imaging spectrometer that was sort of half aerospace, half military. And when we wanted to do the validation of that instrument, we were going to use Lunar Lake Playa, which we'll talk about in a second. It was flooded. Lunar Lake was flooded the day we wanted to do that campaign, so then it was a readjustment and a scramble, and we just ended up at Ivanpah Playa. And once you go to one place once, then it becomes one of your sites, and you just keep going back to it over and over. It becomes habit. But it was the first of the bunch where we had something that was really flat, extremely uniform. You have the little cracks and things and such in the surface. It's a clay material. Yes, there's illites and montmorillonites and some other ites in there, zeolite and things. And there's a hotel casino that's not too far away. So the students that I had loved it. Just to really put it in perspective, when we travel the United States, we get money to travel. So we get hotel money and we get food money. And out here it was based on the Las Vegas travel costs. So the hotel would be $100. We never made up that money, but the food costs. If we had stayed at the site and camped out, we would get $30 a day. But by staying in this casino, we got $65 a day for food. And there were not any good restaurants, so we made a lot of money on food on those trips. And it was managed by the Bureau of Land Management, which limited access to the site, which could be a good thing because it limits who can use it. The bad thing is it means that you may not have access to it. So there have been many times we've gotten there and the gate was locked and we were not allowed to go out onto the site. But its flatness, both in spectrum and in spatial uniformity and everything else, was excellent for us. So then the next one was Lunar Lake. And this one sort of was between the two. It really came before Ivanpah, but we never used it until we went to Ivanpah. And this was found because Phil Slater served on a PhD committee defense. And the student was doing Mars research. So this starts to show how things can kind of tangle up. And to do his Mars research, they were flying avarice over a crater, a lunar crater. It was called Lunar Crater, but it's a basaltic flow up north of Lunar Lake. It's right over here, one of these volcanic craters. And he wanted to calibrate avarice during the same flight. And really what he was trying to do was a spectral flat fielding. Because we knew that the spectrum here in the bands he was interested in was flat, and so he made sure that his flight lines went across Lunar Lake and then over to his test site. And so he had some way to do a flat field, because this is back in the late 80s, early 90s. Avarice circa 1993 was not very good. So having that calibration allowed him to graduate. Slater asked him about, is that site available? Is that accessible? And when he saw it, he said, well, maybe we should try using it. And the problem was it was quite a bit further from Tucson. So here's Ivanpah Playa, and there it is all the way up there towards the top. And it's tucked away, you'll find out in a second. It's tucked away right next to Railroad Valley. It's right here. And that became the site that we used for several multiple round robin experiments, where we brought in international groups from a lot of countries, went there. Uniformity is excellent. It's the most uniform of the sites that we have. It's very flat. It's very small. So it's only really good for 20, 30 meter resolution. Beyond that, it's a bit difficult to use. The other problem is you cannot use it in the winter because it floods every year. The reason it is so uniform is because all these mountains over here send water down with sediments every year. And all the sediments in here get redistributed, and it just flattens out and it becomes very uniform. But that means you're only really able to use it confidently about 3 or 4 months out of the year, and that's a problem. So it's small size, and the fact that it wasn't usable all the time, because again, if I'm sending students on trips, I want to have some kind of easy repeatability. I want to be able to say, here are your directions. I don't want to say, okay, we're going to Lunar Lake today. Here are your directions. If I have two sets of directions, I might give them the wrong one. They end up at Railroad Valley and they go, I have no idea what he's talking about. 1 kilometer size? This thing's way bigger than 1 kilometer. I wish those were not reasons, but they are. So then it became, we want to do MODIS. The French would like us to do vegetation, 1 kilometer footprints. We need something bigger. We were driving to Lunar Lake and went, what's that? So here's Lunar Lake over here. The road is basically comes right along here. So when you go to Lunar Lake, if you're coming from Ely, you come down, you go past Railroad Valley, and you come in through here to get to Lunar Lake. And Lunar Lake, if you were leaving at the end of the trip and you want to take a shortcut, you actually came up and around and went down the backside to avoid some traffic in Las Vegas. And so we noticed this really weird thing and said, well, maybe that could work. Started getting some imagery and said, yeah, pretty big. We can get, this is about 8 kilometers across there, so we can get some multiple MODIS pixels. The is much better than what we had at White Sands. So again, I'm doing a mix here to try and bring out some colors, and it really ends up being whitish, grayish, brownish type material. It's not a difficult site from a spectral standpoint. It is one of the more interesting. And usually, for whatever reason, I didn't have my extraterrestrial highway sign on this one. But I do have my, in the United States, we have what's called open range. Open range. There's no fencing. And so the cattle can go wherever they want. And it's funny is there's 2 sets of signs that they use. They have one where the cow is just standing. And then they have what we call the dancing cow. For some reason, we just thought that was very funny. And then one year we were driving up and somebody had gone and painted flying saucers on all of the signs. And the reason is because Railroad Valley is just north of Area 51. Now, for most Americans, they know what Area 51 is. In China, I'm not sure if there are these odd places where secretive type work happens and people are not really allowed to go in and nobody talks about them. But you see odd things, like we were out at the test site one night, we slept out at the camp, and they were doing, and it's an Air Force base, is Area 51, and they were doing low flights, and they were dropping flares out of the aircraft. And it's just a very odd, and you hear sonic booms on a regular basis. It's just a very odd place. The city of Rachel is on the way to get to Railroad Valley, and that's where the Little Ale Inn is. And if you say Little Alien, if you have access to the movie Paul, it's a really bad movie, P-A-U-L. It's all about Area 51, basically. But it's a humorous movie. It's very funny. It'll give you insight into this sign. And it makes it a little bit easier when you get out and you're basically walking on this kind of squishy material. It's not hard, so it's very difficult to walk on. Your shoes, you typically will wear, instead of low shoes, you have something that covers your ankle, but that dirt just gets inside there and just gets caked. At the end of the trip, you just have mud all over the inside of your shoes. But from a remote sensing standpoint, it's excellent. The problem was that site then led to us saying, we know why this is a good site, and here are the reasons why Railroad Valley is a good site, and that led to then what are the kind of parameters you want for site selection. Yeah.
Go back one slide. Yeah. Go down forward here. It looks like there with that material, shadow too, right? So as you're walking around, you're getting some mix of shadow and right.
Right, and so one, that's okay because it's random, and the idea as long as you're sampling it, you're in good shape. And we found that as long as you get 5 samples, that's sufficient for you to characterize both the cracks, there's a white material, a salty material that's on top, and there's some of the areas it's fairly common or widespread, but you get that sampled along with the typical background material, and you get some of these bumps, kind of the macro scale lumps and bumps that cause shadowing. And one of the reasons we like taking these photos from the edges, it makes them look like they're kind of walking on air, but also you can see really the vertical nature of the material. And that does play a role, especially with low sun, high solar zenith angles for the sun. That can give you a BRDF effect. when I was doing the backward look results for Astor, we had issues with that, and that's what was causing some of that hotspot phenomenon. So in terms of, if we're going to talk about what are the characteristics we want for a site, it helps to know whether or not man-made is more important than natural. There are good reasons for both. The advantages of man-made is you pretty much have better control of everything, except for size. It's really hard to get a large-sized man-made site. Now, there are ways to do it. And one way to do it is to mow grass. Golf courses, technically, I think would be a even if it's a natural area, you could call that a man-made site. This region here, which is up the South Dakota State Group, near Brookings, South Dakota, there's a company that allows them to use their grassy field behind the factory. And they asked the company if they were allowed to mow it. So just before an overpass, they would go in and they would mow an area to shorten the grass, but that creates a bidirectional reflectance effect. So you have something that's nice and it's uniform in terms of the height of the grass and it's uniform in terms of the sampling, but you have a strong BRDF, as well as with these fabrics and the tarps, and these are mirrors over here. But what's nice is with all of this, you can control the radiance levels much better. So the mirrors, typically, if you're using them for radiometric calibration, you're using them in a sub-pixel format. So the size of the mirror defines how bright a pixel you're going to get. So you can go anywhere from a 10% effect to an 80% effect in terms of the output of the sensor in that one pixel that's lit up. Here they're using it more for spatial assessment of the instrument. Likewise with these blue tarps, they're doing it for spatial assessment. This is an Iconos image, or QuickWord. This is a QuickWord image. So it's a 1 meter spatial scale, to give you an idea. So these mirrors show up really clearly in that situation. But you have much better control, but at the same time, you really can't get things that are very large. The 25 meter size fabric tarps, more than 4 people deploy them. And they are really heavy. And if you buy, let's say, 4 6-meter tarps and use that instead, well, now you still have to have 4 people to carry those around because you don't want to be carrying one yourself. And it takes a while to deploy them. You've got to match them up and hope they're identical and they're different lots, and you've got issues there. The way they make those tarps is they weave in metal fibers into the material of the canvas. And that's how they control the spectral response. Because for them, it's more important to make sure it looks good spectrally, which means they have no desire to worry about the bidirectional reflectance effects. And that's what then creates a lot of issues, is depending on what the sun angle is, you get a much different reflectance. The folds of those tarps can create some interesting features as well. So when you're talking about the surface structure of Railroad Valley and causing shadows, you have a fold in your tarp and you have some interesting features. If you're cutting grass, it's the same thing. The other problem is if you go ahead and find another place like a parking lot, an airport, or a golf course, or parks, people like to use them for other things, which means you might not get access to it when you want, and there might be things on it that might cause problems with your calibration. So, advantages and disadvantages to man-made type objects, and I apologize for the term man-made. I didn't come up with people-made. Just sounds a little too stilted, and unnatural sounds biased, and so we're trying to get better at not forcing everyone to think about genders and such, but at least I know it's there, and I apologize for it. Tarpaulins as a site, again, they're very nice, flat reflectance. You can get different brightnesses, but getting them laid out, and here they're trying to piece together a couple of them, and to get the 25 meters that they want, they basically bought 6 or 7 meter systems that were 25 meters long. And they would then roll them up on a spool, and they had a forklift that would catch the spool, and then they would roll it out with the spool that way. So it was, they had ways to do it, but when you go on grass fields, it's a little trickier. You can put them anywhere. That's really the best thing. The group that's using, I think, tarps to the best advantage now is there's the folks at Digital Globe in Colorado. Because Colorado is a nice clear atmosphere location. It makes sense for them to do their calibrations near their plant. Why travel someplace? You already have the atmosphere really clean, you're at a high altitude, and they have high resolution instruments. And so they just store their big tarps in their factory, and it's not a factory because they don't really build the instruments, they just process the data. But they have their laboratory, and then they store them in the laboratory, and then they have a forklift, they pull them out, they deploy them on the parking lot, and they control the parking lot, so they tell people, don't park here today because your sensor that you're working with is coming over, and everybody's happy. In fact, what happens is you get a big party usually, because where they know the tarps are, then they start going out and holding up signs, and they start making, they get like 20 people, and they start spelling out words and things. It's a lot of fun. So it can be done if you have the, it's a fit for purpose type of system.
Can I just throw reference for a thing? It's important that they're not transparent, or do you measure them on site?
So everyone that I know measures them on site. It is because of the BRDF effect.
Yeah.
The transparency is minimal. It would be a problem if you were putting this one on top of snow. You might see some kind of transmittance there.
And you don't see vegetation and do that, no?
Say again?
You don't see the vegetation effect.
No. You do see a vegetation effect on this one. But most people, and I tend to agree, I would attribute it to adjacency effect.
Okay.
That you have scattering coming from outside.
Can I say something?
No.
Sorry.
She asked. Okay, go ahead. They seem to be interested in what you have to say.
Thanks. I just want to comment on Chris's question, because we did that a lot when we were young and I was very naive. Yes, the tops, a lot of them actually are quite transparent, Chris, and we
Just getting some water.
and we measured them in the lab, we measured them in the field, and in the end we ended up actually stacking quite a few tops on top of each other just because of that transparency effect. So we ended up stacking a black, not top, but plastic type top on the base, and then stacking a white top on top of that. But now that I'm so old, I really cannot physically do those tops. They are a real pain.
Yeah, and the nice thing with the Digital Globe folks is they have their normal workers that work the floor and things. So they have people that are big and strong that deploy them for them. So it's really the best setup that I've seen. It takes advantage of the concept of man-made targets, which is you can put them where you want them. You know, you get to derive. What's interesting is these came from Mississippi. So you start talking about, we're going to bring a set of black and gray tarps from Mississippi to South Dakota. And it was just because they wanted to be up in South Dakota because the other group was doing spatial analysis. But it doesn't take advantage of having tarps. You want to go somewhere where it's clear. So that's the same picture I showed already. Also, you can use asphalt. I've shown this multiple times. Folks have tried to use runways or tarmacs, parking areas for aircraft, concrete. It turns out concrete has a very significant BRDF and a seasonal change, depending on, outgassing, I guess, or some other things. Asphalt is really weird. It is probably one of the most Lambert-ian surfaces I've ever come across. Unbelievable. And the odd thing about it is it doesn't change with illumination angle. And as near as I can gather, it's just because of the size of the pebbles and things they have in it, and plus the fact that it's all filled in between it. It's this kind of perfect combination of a bulk and a surface scatter. It gets rid of things. I may be wrong, but we tried to find a BRDF from the data we collected at our test site, and it just never showed up.
Would you comment on runways? Because that's what we're using for our airborne sensors for years and years. Interesting thing is that during one of the Earth conference, a group from, I guess, Southampton airfield were actually measuring it on a daily basis.
Yes.
But what they found out that even though it's asphalt, you think it's man-made material. You've got lichens and these algae in, so you've got a changing reflectance over the day, just because. And these algae and lichens, they don't have any features when they're dry. But whenever there's humidity, they start to get photosynthesis within half an hour, and when the humidity is left, they stop. If you think you have your runway, which is very nice and stable over time, you're totally wrong, because they are really lichens living there, changing, reflecting. So you can characterize your airstrip, but you still need to do it for every calibration. Still a good target, but you need to go out, calibrate during the overflight. There's no way around that.
Now I can tell Alex Getz why he had problems with runways. Because he tried to do that for Landsat 7. He was going to use them as invariant sites, because there were a lot of them in Colorado. And it just never worked. And we figured most of it was BRDF, but that makes a lot of sense. Because at White Sands, you see algae and spectrum at White Sands as well. Natural sites. Basically, three that we've been showing over and over and over again. You see that I recycle graphs and figures a lot. Natural sites, what's nice is it's the only way you can get a high reflectance and a big size. And even Ivanpah Playa at 1-2 kilometers, I consider this to be a small site, but when you start comparing it to a 25-meter tarp, it's enormous. So the only way you're getting bright and big is if you go to something that's natural. We still have not found anything that is reasonably good that's big and black. The ocean's okay if you can get away with the specular issues, and you don't need to go to all the wavelengths, and you can deal with some of the other features of it, but it's difficult to do absolute radiometric over water. But finding a flat surface that's less than 0.05 reflectance, that's reasonably stable, if anybody finds one, let me know. We've not done a global search for it, because all our global searches go at, for some reason we picked 0.4 reflectance. I don't know why anybody would use 0.4 as a guideline for large site searches.
Don't know. Someone told me. I read it in some paper somewhere.
You could make a site that was in the 3 kilometer. I figured out what it would cost. I even figured out what it would cost to spread powdered halon over a 3 kilometer by 3 kilometer area near Tucson, Arizona. And it's really reasonable. It came out about $250,000 US, $250,000. That's all. That my budget to run my group was 4 times that. And of that, a significant fraction was just travel to these test sites. And if you had something that was truly traceable, I mean, a 3 kilometer object that was, if you pressed it properly, would be perfectly traceable. We had some issues with the argument that the reason we were going to destroy a 3 kilometer by 3 kilometer area of ground was to study environmental satellites. So we really did not try very hard. The regulatory aspects of it, I know that there's a group that's working about tow here in China is now starting to try and smooth out a region of some of their desert area to come up with something that's reasonably large size that they can use that's fairly flat, natural material. The natural sites, typically you can find them, but if it's not in an area where you have clear blue skies, you're stuck with where it is. So it just is lucky that Lake Tahoe is a nice, very large lake at a very high altitude in a nice ski resort area. It just was, whoever started using Lake Tahoe just was lucky. Railroad Valley, this is as close as you're going to come to being able to swim at Railroad Valley. The structure, as was pointed out, there's some interesting little features. The white material, the brown material, and then it's also undulating. Ivanpah Playa, this is the typical, what happens is when the clay materials get wet, they spread out, and then as they dry, they basically start to clump together, and then it causes the cracks. And that's something you have to make sure that you take into account. You will get a BRDF effect because of this. But it's usually at only very high sun angles, and where you're looking near the hot spot is where you'll see that. Disadvantages. You're stuck with where nature puts them. So in the case of Ivanpah Playa and Railroad Valley, we were 7 to 10 hours drive to Ivanpah and 14 to 16 hours to Railroad Valley. And it just limits what you can do and how many people you take. Spatial non-uniformity, you don't control that. and the surface microphysical properties. So the point that was raised about the cracks and the bumps and things, now you have some things that you have to be able to measure. Key parameters. So test site selection. Goal in the selection is basically to reduce our uncertainties. So critical choice that allows us to do that. I'm sure Cindy has a better list because she did it very careful. She grabbed the paper. I've simplified my life in terms of how I view it as high and flat spectral reflectance and nearly Lambertian. So that's roughly the material that I want. Something that I don't have to worry about angular effects, I don't have to worry about spectrum effects, I don't have to worry about the low reflectance causing me problems with the atmospheric conditions. Large size and spatial uniformity. So that makes it easier for me to measure. It also means I can ignore adjacency effects. What's nice is we also tend to pick places that are low aerosol loading, and that removes adjacency effects. The accessibility and the historical understanding. The fact that I like to tell stories tells you that this one is one of the ones I start with. If I know nothing about a site, odds are I will never go to it until somebody else does and tells me about it, because I have access to sites that I already know about. And even now, being at NASA Goddard, completely on the other side of the United States, it's still easier for me, and there's a chance that I might in 2 weeks be at Railroad Valley doing measurements for an airborne flight. I will take a plane to Tucson, pick up the equipment of my old group, because they'll let me borrow it because they think I'm trustworthy, and I will drive to Railroad Valley. It's just because it's easier than it is for me to try and find something on the East Coast to do a similar type of campaign. Considering that my two colleagues from Japan and periodically joined me at Railroad Valley, and I think you were just there in January, correct?
Yeah.
Yeah, so they're coming from across the ocean to that site. The range of transfer code, the aerosol models, everything else are important, but how important they are dramatically is affected by what you choose for your test site. So we can reduce uncertainties, atmospheric uncertainties, they're lower, and I've shown this already at the intro, and now you've had enough kind of other material with what Martin showed and with what I've been showing that if we go to high reflected surfaces, the atmospheric compensation we have to do is much smaller. The effects of the atmosphere are much smaller. Low aerosol amounts also. If I can find a site where I have a clean air, then that's a much better place to be. Whether I can find those things everywhere around the world, that becomes part of the problem. The reflectance uncertainties. If I'm spectrally flat, that makes it easier to do the band convolutions. It makes it easier for me to characterize it. Spatially homogeneous. Now I do not have to make as many measurements. I might be able to now, especially if I want to change my methodology to maybe only do 15 samples, I want to make sure that 15 samples is enough for that site. Clear skies. If you're physically going to the test site and it's a 15-hour drive, high probability of success is a very nice feature. And then the higher altitude again, the amount of atmosphere and typically the amount of aerosols go down, and the large test site is reduced adjacency effects. So we can look at it from just a view of the atmospheric conditions. There is, I forget if it was exactly this one, but you've seen something, so there is no perfect site. You will never find it. And I'll tell a story about our efforts of trying to find a site in Tucson to illustrate this. Smaller sites, adjacency effects, but maybe it's close enough. So we were far from Tucson, so we decided we were going to look for a small site. Let's see if we can find the perfect site in Tucson. Odds are good we're not going to know that there is one because most of the others we found because we were driving by them. And so I drove around Tucson all the time, and I wasn't all of a sudden going, oh, there's a perfect site. High reflectance can be sensitive to aerosol absorption, which is really hard to characterize. And this was the thing that bothered the people early on with the Arizona group was they thought they had to develop an instrument to do a complex index of refraction and retrieval. Low reflectance sites, now you're more sensitive about aerosols. Urban sites, range of aerosols. You can be polluted or not polluted. Rural sites, they're hard to get to. That's why they're rural in our definition. if you get anything at all from this discussion of 3 days, and I apologize, I tried to put it on the first day so when you were still awake, and we're kind of drifting now towards the end of going to a break here in the morning of the third day, your best approach is to understand what is happening. Conscious decisions are good, even if it means you have a large uncertainty. You just want to make sure you know that you're making that decision because of the large uncertainty, that there's another underlying reason for it. Maybe I can get more data, and that uncertainty I have that is large is truly random, which means that if I can get 4 measurements, I get a factor of 2 improvement on that uncertainty. If I get 9, I get a factor of 3 improvement in my uncertainty. Roughly, that's, I'm mixing statistics there with shot noise and normal distributions, and I know I'm doing it, but it's still, it makes sense to us. If we can average things over numbers of data, we can beat down our uncertainties. So, I want to talk a little bit about the Pima County Fairgrounds. And I've been talking about the Pima County site, the Tucson site, the small site, the racetrack site. And this one now I'm calling it Pima County Fairgrounds on purpose, because there's a reason why the fairgrounds is important to the story. And we started, as I mentioned, we used it for Landsat calibration. And we used it pretty successfully. I think I have I'll go with this one. And we use it pretty successfully in terms of when we get results, they compare pretty well between large and small sites. We had some differences that we never quite figured out exactly what the cause of the differences were. Could have really been because, this is something to bring up, is maybe the small site's better because we were doing more frequent panel measurements. And the ASD results are actually better than the ones we were doing on the large site. But what we had was we had full scene imagery of Landsat. So I tasked several students and myself. We sat down and said, okay, let's figure out the criteria for a perfect site. This is about the time, this was before the famous Karen Scott paper of Railroad Valley, and she kind of codified some of the things we did. And when we sat down and listed what we thought the perfect site would look like, we went, all right, there's nothing in Tucson, or nothing within 100 miles of Tucson that fits that. The closest we had was a dry lake bed about 100 miles away, but it was always flooded and was hard to get to, and the reflectance wasn't that good. So then we backed off on the requirements, and we said, what I need is a site that is 7 pixels by 7 pixels in size for Landsat, so 200 meters by 200 meters in size. 0.2 reflectance. Cannot vary by more than 0.02 in reflectance over the year. And that basically was the requirements. And the task to the student was, and it had to be that in all wavelengths. The task to the student was, take the Landsat data, and we're only going to use a Landsat scene. So from the whole entire scene, look for all areas that are 7 by 7 in size. We had a uniformity criteria. It could vary less than a standard deviation of 1 dN. So when you average the 49 pixels, you got a 1 dN variability, which is not, for an 8-bit system like Landsat, it's not that stringent of a requirement. It's a fairly large variability in reflectance. And the students searched 3 years worth of data, of Landsat data, which was difficult to get at that time. So we're doing this in 94, 93 time frame. So we were somewhat limited in computer power, somewhat limited in access to data. But we had about 20 Landsat scenes, and they were clear, sky Landsat scenes. Went through them all and said, give me all the 7 by 7 pixel areas that you can find. And one place showed up. And let's see if I can put the pointer. There we go. One place showed up. Right up in there. And it was, I forget exactly where it is, but that ribbon of brown, that is a sand riverbed. So in the desert in the United States, we have what we call washes, that they only have water in them when it rains. When it's not raining, then there's nothing happening. And there are some places where they get fairly wide. And the 7 by 7 it was an area that was surrounded by, it was really weird. When we went out to look at it was, you had about 100 meters of actual sand, And then on either side, there were 50 meters of sand, but there was this big sloped wall. And so it was basically a sand area where they had been pulling out gravel. And then they had the actual riverbed in the bottom, which was the true uniform piece. So you had this wall that you had to worry about because you had reflections coming off of it, but it met the requirements. And we took a look at it and said, this is not going to work. There was no way for us to put digital elevation or put slopes or put in the fact that, no, we cannot have something that's separated by 10 meters in height, because that just really makes it hard to characterize. So then we took it to 5 by 5 meter, or 5 by 5 pixels, which then got us more of these areas along this riverbed. And they were still difficult to work with because of the surround and getting to them and just the material itself, the BRDF features. And at that point, I was getting really frustrated because if you give a project to someone else to do and you're a manager, you always seem to think that there's the right answer and that you know what the right answer is. And I knew there was a site, and I just didn't want to tell them where the site was. And I knew there was a site because I'd been there. I went to the fair, and the fair I'm going, well, this would be perfect. This has got to be a perfect location for doing vicarious calibration. So I'm sitting there going, the student has to be doing this wrong. So what question can I ask to prove to the student that they're not doing it right? And to basically get us to where we got an answer. And finally I just went, please just figure out and just compute the 5 by 5 pixel reflectance DN average for every region in this area and the standard deviation. And let me know, which ones meet at least the standard deviation criteria. And sure enough, when you do that, these two areas showed up, as well as an area that was over just off of the scene right over here that was dirt. It wasn't paved. It was just dirt parking area that we used for the fairs because it was a really popular event in Tucson. Because everybody went to the fair. They had fun rides, roller coasters and Ferris wheels and cotton candy or candy floss, and so it was pleasant memories. So I wanted a test site there because it would be enjoyable to be there for the fair.
Did you ever figure out why the student didn't catch it?
Well, it wasn't the student's fault. It was our fault because the reflectance of band 1 of Landsat for every material in Tucson was lower than 0.2. If I then make the criteria 0.18, the whole, bunches of areas just light up. It's just, it was one band, one criteria, and we were damned because I have 10 fingers. If I had 9 fingers, I would have gone 9, 18, 27, 36. I would have said, I want a reflectance of 0.18. If I had 8 fingers, like on The Simpsons, anybody a Simpsons fan? If I had 8 fingers, then I would have looked for 0.16 reflectance. But because I have 10 fingers, and I admit these flaws. We biased our search. The 0.4s we'll see it's because we have 10 fingers. It could have been 0.35, at least that still matches the 5 fingers. But that then became a case where we sort of knew that there had to be something available. And the reason why we just said, and then we could have then reallocated the search again. But what was nice is the area that I knew about that was publicly available, easy to get to, was not right in the city, was located in a good place. All of the other factors that made it a good site in my mind, at least it was from a scientific standpoint justifiable because of its reflectance characteristics. We had to get collected. We had to get practice. The launch was coming up, and so it was, okay, we're not going to look for the perfect site any longer. We're going to take the site that we know matches our criteria. It may not be the best one for that case. We might be able to find something with better standard deviation. But I don't know about the accessibility and all the other things related to this. We'd already been talking to people who run the parking lots. We knew when the races were happening. We'd already figured out what the day of the launch was going to be. We had to get practice. We had to get historical data for this data set. We had to get the students out there and get them used to driving to the site, parking, setting up, figuring out how we wanted to sample it. And so while we did this the right way, back in the 90s, as best we could, eventually we reverted back to, we got to get something done. Not good, not bad, but we still were able to figure out what the inconsistencies might have been because of that site. We knew the reflectance would be, and so this is what caused the problem, is everything right down in here. So here's point 2 reflectance, that was our criteria, and band 1 of Landsat, right there. Small and large site, talked about that. Site selection and accuracies and uncertainties, so this is the last bit for this section 10. And then we're going to hand it off to Cindy, who's going to go into her discussions about the really good work. In other words, the most, there have been 2 scientific searches for test sites in the last 15 years. The French did it for the Libyan desert work that they do, and this person here for Australia. So what I'm trying to do is lay the groundwork for that. And the whole idea is, what does the site actually do in terms of causing uncertainties? And in one case, it's how do we have to sample it? And this is a very strong stretch. I think it's over like 3% total. So basically, this black thing here is 10%. This black piece here is 10% different than the whitest part. So it's a very strong stretch. It brings it out. But we're only sampling things at a small scale. The question becomes is, how well do we have to sample it? Well, 4 random picks across this area at the 1 meter scale is sufficient to characterize the entire area to better than 3% in all cases. And that's the 99.9% significant confidence level. Just enormously confident. If I go to 1%, then I still get it at much better. It's at the 95% of 1%. But it tells you that if we get random, we're in good shape. If it's too random, then it just doesn't look very good. It makes it harder to work with. It's just safe if you oversample. How big an area you have to cover, that affects how you sample. We talked about this a little bit yesterday. The goal is that you want to get, and this is what sounds odd, we want to get to a point where the surface is not dominating the measurements. Or, I'm sorry, the surface and uniformity dominates the instrumental effects. It just, and it's bad, and that's why I always get it wrong when I describe it. It's only talking to Nigel Fox, and he's been able to convince me of this, is you want to be able to drive all of your uncertainties with your sight as opposed to the instrument. Because that allows you to characterize the instrument uncertainty on site or even in the laboratory and not have to worry about what it's doing. Eventually, if you get to where the instruments, the dominant cause will be in really good shape. But for now, it really is, you want to make sure that at least your sampling approach is the site itself is the dominant source relative to the instrument. So I want to make sure it's the instrument on the ground. But you can still reduce the impact for the instrumentation and the other air sources by doing this. Size of source, both stray light and adjacency effects are impacted by the site that you select. The reflectance will impact your uncertainty budget for the site that you select. If you pick the magic reflectance, that's really nice. If you can get away with that, you can find something that's in the 0.3 kind of reflectance. That makes your life easier from an atmospheric standpoint. The flatter your spectral reflectance, the easier the band convolution problem becomes. And by easier, I mean you do not have to prove to everybody how well you're not aliased or whether you're Nyquist or not Nyquist. You just basically say that it's flat. And it's flat to within 0.05% over 20 nanometers. I'm not worried about the reflectance or the band convolution. But this is still not all of it because that reflectance gets multiplied by a solar irradiance and it gets multiplied or included with the instrumental effects and the atmospheric effects. So those will impose some variability. So if you're going to be doing radiance, it's good to have a flat reflectance, but you'll still have a band convolution error because of the wiggles in the solar curve. test site itself does not affect traceability. This is a nuance in language. If I have a really bad test site, I can break my traceability, yes. But it's not the site's fault. It might be the site's fault that your traceability is really bad, but if you break it, that's your fault. That means that you did not characterize the uncertainties properly to follow the path. That might mean that you have a very large error bar to maintain traceability because you just do not understand it. But the site itself is not the problem. It's how we do our error budgets that can break the traceability and the pathway to traceability. So the test site isn't causing your absolute uncertainties. It can impact what your absolute uncertainties are. But it's, you can always find a way to get around it. And this is leading into is the site's important, but it's more important that you know what is happening with the site, what the site is doing to you in these situations. So test site selection itself, all of these sites here are just as traceable. I'm taking a panel that was calibrated in the lab to a NIST standard. And I'm going to each of these 3 sites. They all have the same traceability. They may have different absolute uncertainties in predicting top of atmosphere gradients because of each of the specific pieces of things wrong with them. Like in the shortwave infrared, now I have a spectral uncertainty that's larger because I have a lower reflectance. The size, I'm not doing an adjacency effect correction, and so I now either will break my traceability because I completely ignore that, or I have to put in an uncertainty term that's much larger than what I need because I haven't demonstrated it's not an important feature. Railroad Valley, it doesn't have any problems. So it has its features there as well in terms of the aerosols, and whether it's a smoke day or not a smoke day. And again, I can break my traceability in that situation if I do not include the smoke as part of my air treatment.